Okay, we have a series here, and first of all, before we find if it converges or diverges, we have to figure out how the series actually looks, expressed as a sum formula. So we're starting at 1, right? So we might as well start it at I equals 1, or n equals 1, whatever you like. N equals 1. And what's happening here? We have something which is being cubed, right? And remember, with a series, we're plugging in integers, the very next integer. So this one's actually very simple. We're just cubing, so this would be n cubed, right? Because our first term is 1, but then our second term, it's like plugging in 2 here. Our next term is like plugging in 3. So this would be 1 over n cubed. We're going to infinity because of those dots over there. So this is how it looks. This is how it looks. And if you know about a p-series, so if you know about p-series where you have 1 over n to some power, to some exponent, you know that as long as p is greater than 1, if p is greater than 1, this is going to converge. So we already know, if we know about p-series, that this is going to converge. But we are in this integral section of the book, so we have to do the integral test. With the integral test, you make sure that whatever you have in there is always not negative, no matter what you plug in, and you make sure that it's continually decreasing, that the sequence is decreasing, so each next term is smaller than the previous term. So yes, this fits both, because no matter what we plug in, you're plugging in a larger integer. That means that the denominator is getting larger because it's being cubed, and the term itself, with each passing moment, is getting smaller. So it does satisfy that condition. It also satisfies the condition that it's never negative. We're plugging in positive numbers. So given that, we can do the integral test. Let's do the integral test. We just take the integral 1 over n cubed dn. We can change these to x's if you want. I'm just going to leave them as n's. And now we just do n to the negative 3 dn. We add 1 to that and then divide. Negative 2. So that's what we have, and we're going from 1 to infinity. From 1 to infinity. We can't work directly with infinity, so we change these to t's and use a limit. Limit as t approaches infinity. Limit as t approaches infinity. And limit as t approaches infinity. And this is being evaluated from 1, which we got from knowing that this started with 1, so we knew that we had to start our series at 1 in order to make it work. I mean, we could have done a different look over there and started it differently, but this is just the simplest way. And this goes to t. We subtract our lower bound from our upper bound. So with our upper bound, we have negative t to the negative 2 over 2. Our lower bound, we have 1 over 2, and it's negative, so negative 1/2. That's because 1 to the power of negative 2 is just 1. 1 to anything is 1. So we have our limit as t approaches infinity. It's clearly in the denominator that infinity resides because we have a negative exponent, and therefore this goes to 0. This goes to 0, and our answer would be positive 1/2. So this would converge to positive 1/2 by the integral test. Converge.